Kumar Behera with us from IIT Patna. So, Dr. Ranjan Kumar Behera is with us today for the today's program. I will give just a small introduction to Dr. Behera. Dr. Behera is an associate professor in the electrical engineering department at IIT Patna. He has received his BE Engineering degree from Regional Engineering College Rourkela and MTech and PhD degree from Indian Institute of Technology Kanpur, India in electrical engineering. He worked at Hindustan Aeronautics Limited as the trainee engineer. Since May 2019, he has been the faculty member at Department of Electrical Engineering, IIT Patna. From July 2008 to 2009, he was a visiting scholar with the Energy System Research Center, Tennessee Technological University, USA. He was also a visiting research collaborator at Electrical and Computer Engineering Department, University of Pretoria, South Africa in 2016. Dr. Behera received the Young Scientist Award in Engineering Science from the Department of Science and Technology, Government of India in year 2001. He was selected as the Bhaskara Award Advanced Solar Energy Indo-US Science Technology Forum in the year 2014 and as a featured engineer of the Globe of 2015. Dr. Behera has been selected of his biographical profile for inclusion in the new Who is Who in the World 2013. Young Scientist Award in the Engineering and Sciences for the High Power AC Drives for the Electric Locomotives and the General Purpose Highway Application by Department of Science and Technology in the year 2011. He is one of the active member of the Bhakti Vedanta Club IIT Patna, which is working for the poor people in the nearby areas of the IIT Patna. Sir, I welcome you on the behalf of Department of Electrical Engineering NIT Patna and the ATAL Academy of AICTE. So, sir, thank you for being with us here in the today's program. That is very nice experience for all of us. So, I think
thank you for. Although I am not so qualified, but still I try to speak something. So thank you, Ambarisha sir and Bimlesh sir, both of you for inviting me.
Yes, sir.
Sir, can I share my?
Yes, sir. Yes, sir. You can share your slide now.
Okay. So, thank you, Ambarisha sir, and I'm very thankful to you that you invited me for this talk. And today I will speak very whatever research we are doing and a little bit about drives and solar grid integration. Mostly we do a lot of hardware, the project oriented development of the solar and electric vehicle, electric drives for industrial application and vehicular. So today I will give an overview of electric drives and we will go starting from the fundamental drive up to simulation of the advanced drive. Okay. So if time permits, we will also look in some of the applications in this area. So the power converters are very important, and although it is very difficult, for example, solar converter and drives power converter, there are a lot of difference. In the drives converter, only the inverter will work to control a AC motor, or a converter will work to control a DC motor. But in the solar, we need to have a different protection system which is embedded in the solar converter. So that is how it is very challenging. So this is a few whatever already told. And our main research activity: solar, wind, power electronics, drive, wireless power transfer, smart grid, electric vehicle design. And we do also the multi-phase drives and LED driver, wireless power. And we have a book this year it came, the power electronic drive and advance. So today's talk is mainly simulation and experimental study of a grid-connected LCL filter with active damping. Because when we go anywhere, we find out there is a simulation study, and the simulation study are maybe you can say that there is a just a DC-DC converter interface with the inverter and connecting to a solar. But in this study, why I have given, because here both grid connected system, filtered design, as well as the active damping system. So three are modeled and simulated together. Then I'll give an introduction to drive, starting from the fundamental application up to advanced drive like multi-phase, multi-level converter design, the simulation and implementation. So first, the single phase inverter we will discuss. This is a single phase inverter. DC side is our solar, and we have a full bridge inverter circuit. And through LCL filter, we have connected to a grid. There may be directly connection, or there may be interfacing transformers also connected at the grid end. So this LCL filter and inverter and this grid connected system, we generally come across three frequencies, which is very important to understand. First frequency is the switching frequency of the inverter, at which all these power switches S1, S2, S3, S4 are operated. And these are operated, S1, S2, or these four switches are operated. And these four switches gives rise to an alternating current, alternating voltage. This alternating voltage the output voltage is filtered because it is contains a lot of harmonic ripples and the pulsating in nature. So we filter out for getting a smooth AC. Okay, there are LCL filter, LC filter, all these things. So this is a very simple. You can just inverter modeling. You can see U dot VDC. So that way we can easily model this inverter. Then we have LCL filter, and grid. From the grid we get the information of angle, and then we have designed the current control technique. So reference current generation, and from there a controller, PI controller, and we have an active damping. So you need to measure the voltage across this capacitor, and this will give you the charging current, okay, information. So that both they will give you a reference current and then current control technique. By using hysteresis current control, we control this pulse generator and feed to this inverter circuit. That is the basic block diagram. So if you see here, there are three frequencies come into picture. One is the switching frequency of the inverter. Second one is the resonant frequency of the filter. Third one is the the sampling frequency, where you implement practically the system. And these three frequencies are, if you study, I can tell you, so many PhDs can be produced just by correlating these three frequencies. Actually. So this is also very challenging, actually. Which frequency you will take care? Whether you will take care when you design this type of grid connected system, whether you will take care of your regional frequency, whether you will take care of your switching frequency, whether you will take care of your the sampling frequency by which your microcontroller or DSP will run. So in this, all these things, if you see it, this system, it becomes very complicated. But most of the time, we ignore that one. Somehow, if we get the result, we try to find out, okay, this is the frequency by which we can develop this system. But when you have a matching, for example, when we are having a radio station, in the radio station, if somebody is speaking from that side, and you tune your frequency to that station, then you get maximum amplitude or more sound or proper clear sound. Similarly, when the switching frequency and resonant frequency, you match each other, then you will find that there is a maximum power transfer to the load. And that way, we have, this is a complete control unit. And this simple system we modeled here, okay? This is a first order differential equation where you can see 1, 2, 3, 3 elements are there. So third order system. And you can model this very easily. And the switching function U, which is defined here, this U is +1, -1, when S1, S2 is on, -1 when S3, S4 are on. So this system very easily you can implement by using a simulation block in Simulink. So generally we do in Simulink because it is a widely available software and it can be interfaced with any kind of devices. So this system is modeled like this. Then we find out the Bode diagram to find out this filter design. We design the filter with a different parameter, and then we found out that what are these, whether the system is complete system stability as well as other things. You can find out the parameters. So if you see this equation, this is a simple equation, active damping you put. So you can see that the simple equation is the reference current you can obtain by using this one. And the complete unit, you can find out the transfer function. When Vg is equal to 0, you get this transfer function. So when we get this transfer function, then we use a proportional plus resonant control, PR controller, is a proportional plus resonant controller. Why? Generally, hysteresis current control is dependent on the hysteresis, the instantaneous current of the phase. So when both the current are subtracted from each other, you get a profile like a switching, the tracking error profile, like a moreover nearly fundamental frequency, like you have fundamental frequency 50 Hertz. Around 50 Hertz, there are a lot of ripple like the error, everything will behave like that sometimes. So when you are seeing those type of things, you must understand the resonant controller will help you to increase the dynamics of the system. And the complete system dynamic is represented here. With the PR controller is your transfer function into PR controller. Based on that one, we found out what is the switching frequency. So you put the value of VDC and grid voltage and L and the hysteresis band. So automatically we can calculate what is the switching frequency, which is very difficult in case of a hysteresis current control. And hysteresis current control is called, another name of hysteresis current control is variable switching frequency control. You cannot get because hysteresis band is depend on the position and the amount of ripple present in that system. So hysteresis band, you can have a signum function also, but we put hysteresis band to limit the switching frequency of the converter. So if you see, there are two kind of, one is a single band, another one is a double band hysteresis controller. And if you want to know more about this one, recently we have a industry application. It is discussed there. So this one, and you can see that the double hysteresis band, the output voltage is like a plus VDC and minus VDC. So it is like a bipolar. And whereas this one, if you see, the double hysteresis band, that is what is like a unipolar. Okay, unipolar means only one direction. You can see plus VDC. Then in the half cycle, another half cycle will be minus VDC. So this technique is now we used here, and it is modified. Okay, then we modified, and by using a simple the SR JK flip-flop, we designed this complete unit, and it is also, you can see that this is the output. Okay, based on that output, we designed the hysteresis band. Now, based on this one, we design the logic diagram where it will turn on our switches. Okay, all the switches will be turned on. Now, here is your modified hysteresis band. You can see that this is a unipolar output. Okay, unipolar PWM technique. So the same technique we implemented by using hardware prototype. And this hardware prototype, you can see here, there are DC link voltages, and these are the current sensor and voltage sensor, and there are the below, there are the switches and LCL filter and connected to the grid. Okay, these are the parameters at which we found out the grid voltage is 230 volt and DC link voltage is 400 volt. So all other parameters we found. Then this is the simulation result. You can see that single band hysteresis current controller, the switching frequency is very high. As you just make a double band, the switching frequencies are coming down. And you can see one of the thing is that during the zero crossing of this sinusoidal wave, you can see that the frequency is very high in the case of single hysteresis band. And in the double hysteresis band, you can see, or modified one, you can see that this switching during the zero crossing switching frequency is limited. Then you see here, we have current, and suddenly there is a change in the current reference. So you can see that the actual current is tracking it. Whenever you change this current, that is why the current control technique are first dynamic. It is very fast response. As soon as you change, it will change because it depends on the instantaneous values of the current. So that is why These are very popular in implementing the first dynamic type of systems. And these are the few hardware results with respect to that one. We implemented, and these are the hardware. You can see that there is a change in the current, dynamic change in the current. This is reflected on this current also. Now, the conclusion is that it can be improved, and we improved many things in this one. And easily you can, by using this modeling, by using the simple differential equation, you can model the system. There are a few references, and then we will just see a little bit about the grid control, how the inverter are connected and they are modeled. You see, sometime when we see a solar plant, you go there, you will find that the current and voltage are like this shape. Current is like a triangular and voltage is a sine wave. So this is very common in a solar plant. Why? Because it depends on the irradiation. If your irradiation is very low or your load is very low, you will experience like this current wave. So there are a lot of harmonics. So we are not going in detail in this harmonic because our so there are a lot of harmonic standards, European standards, and the American standards, as well as we have Indian standards and IITP at last. So these are, they give that the voltage harmonic must be less than 2%, and the current must be between 5%. So there are other standards which they specifies. The voltage harmonic can go up to 8%, up to 40th harmonic. So with this one, we designed the circuit where we have a solar plant here in IIT Patna. And then this is the structure which we are utilizing the solar energy. That there is a MPPT tracker and there is storage of the battery bank, and then we have interfacing circuit and power detection. It is connected to single. So the main component of the system is the DC link and a Hertz bridge and a LCL filter connected to the grid. So this modeling we can do by using a simple state space modeling, and it is very easily one can do it, and by using equation editors, well, you can easily easily simulate the system with the filter. So you can see that these are just a third order system, very easily one can solve it. And then this is the controller design, because without controller, anything is not possible to control the output voltage, frequency, or power, whatever it may be. So this complete system is implemented. And you can see here, there are the harmonic point. When the load is very low, then harmonic contents are more. When load is high or as per the rated one, then harmonic content is low. That is the what inherent problem of the solar system. Solar system, when you connect it to the load, which is as per the production, means generation must be equal to utilization. Then your converter or your solar system is the best. So if the generation is more, utilization is less, that creates a problem during the utilization. So that when you see, that is why when you generate, our load always remains high as per the production of the solar. Now, when you have, you will see that there is a partial shading or something. Your waveform, the current waveform is so distorted. But when there is full loading condition, you can see that the current is the sinusoidal and in phase with the voltage. And this is the phase current THD. You can see that it is. Now here in this one, you can see that both the current and voltage, red color is your voltage, and the blue color is your current. You can see that current is distorted, okay, always. Why? Because there is a constant partial shading, and where it is properly, the filter is not designed. You can see at light load also you can occur like this. And then we have, when the full load condition, you can see that both the current and the voltage are in phase, and they are also pure sine. And this is the, when the inverter grid, when the grid during the inverter feeds to the grid, okay? Inverter is feeding to the grid. Now, the inverter is taking power from the grid. That means you can see that the current is just opposite to that. So if you see that the conclusion is that here we designed the 10 kilowatt, and it is the sponsored project also. Now we will discuss the electric motor and the drives and simulation and control. So if you see here, this is our electric motor in the industry. There are shunt motors, series motors, compound, and separately excited motor. So I think most of you must have visited many industries. Especially, I put a picture of a hot strip mill in the steel plant. In steel plant, we have a hot strip, and this hot strip mill, what it does, it brings a big hot slab, iron slab, and this iron slab moves from to and fro till this thick iron slab became thin. So very thick iron slab becomes very thin by using pressure from both sides. Whenever there is a pressure, there is ample amount of water sprayed between these two junctions. So that is how this complete this hot strip mill is controlled by using this kind of the motors. So till today we use the DC motor because the DC motor is easier to control. Where the AC motor is a very complex motor, and the AC motor, once the dynamic you are changing, that also affects on the performance of the or the air gap flux, which may demagnetize your system. Okay, so there are four motors which is used in this industry: shunt, series, compound, and separately excited. And this AC motor also, induction motors, synchronous machine, permanent magnets, and switch reluctance motor. So the adjustable speed drive comes from power electronics, machine, load with control. And that is what the main drives is. There are different variable speed drives, that is converter feed DC drives, voltage source inverter feed AC drive, current source inverter fed AC drive, cycloconverter feed AC drive. So cycloconverter, you will be very happy that the cycloconverter is a concept initially given by Professor T. A. Lipo and uh, Dr. Arjit Chattopadhyay from IITP. So this became very popular in due course of time. And then drives, we started using the GTO power based converter, and then IGBT based converters, and that are we used in the EMUs all over India. Okay, so today, if you see, although in India we don't design actually very high power, but we get it from Siemens, Alstom, General Electric, Semicron. They supply these converters to our Indian Railway, and that converter we use for this railway. Okay, and that is how the railway is one of the biggest user of power converters. Actually, if you see here, they required IGBT rating of 3.3 kV and 70 kVA distributed and 115 kVA by Siemens they give. And if you sit inside train, you find there is a big exhaust fan which is connected. That is what cooling system. Okay, complete bogie or that engine is connected there, and all the air it is throwing out that behave like cooling system. And also weight and how it will be. So if you see, this is the structure of a main converter. And if you go to Chittaranjan, like last year we visited with our students. In Chittaranjan, you cannot find inside what is, but the inside converter, what are there, you don't know actually. They will pack it very tightly. You cannot open it actually. So then these are how the complete battery charger, main control, low voltage switching, and all these things are connected there. So drives is the heart of the locomotive, and we generally import all these drives. For example, Shatabdi train, it travels from Lucknow to Delhi. We purchased that one from Australia. And that was the first AC drive was designed, and it was very efficient also. Today also Lucknow and Delhi Shatabdi is, you can see that is from Australia we purchased. So why the high power converter? Like I was in the National Solar Institute in Gurgaon. I asked, what is the maximum rating of power converter you test here? They told that, sir, we have testing facility up to 10 kilowatt. And above that, what a third party they give where we can test it. So in India, we don't develop the high power converter. Generally, we import from outside. But we have a lot of potential, but we bring outside. And then you can see these are the few drives. The main challenge is that you need 4.5 megawatt of the power, around 6,000 HP traction drive. You can see here, there are motors are connected here. You can see motor is connected to directly through the gear, and it's connected to the shaft of the machine. And you need a high power switching converter, fabrication and design, and putting the size must also match. It's not that you can design like in laboratory, we put converters here and there, but we should know how to make it very compact. And real-time controller integration deployment in the actual locomotive. If you see the traction drive, cantilevers and catenary cables, okay, they are connected catenary cables, and there are, you can see here, there are droppers, other things. And what is the main important thing is 4-quadrant of forward motoring, forward braking, reverse motoring, and reverse braking. So if you see, there are many communication network also, which reduces the wire, because in the train, in the especially railway system, the communication is one of the very important for protection and the controlling or management of these running trains. Then we have a open loop drive like this, the DC motor drive, and fed by by a controlled rectifier. Okay, this is a controlled rectifier, and feeding to this DC motor drive, and DC motor is rotated by this. So by controlling the alpha or the firing angle here, you can do this. That means how to model the system. The system can be very easily modeled. Why? Because there are RLC circuit, VDC is equal to RA plus ILTIA by DT plus EB, and that is completely unique. You can understand that this is the modeling. And then this complete modeling you can do by you. And there are also speed controller that is called the cascaded speed control. That means in the cascaded speed control, two loops are there. Inner loop always it is current control, and outer loop is always it is a sluggish response, so speed control. So this way we can do, and then you have conventional AC drive, you have front end as a diode bridge. They draw harmonic current from the source. So now the government of India do not want to use this diode bridge. He want that we should use a utility-friendly converter where it will enhance the input and the output, or the hence that means both the current and voltage will be in phase, okay, phase with each other. There are many different kind of drive, okay. Two-level topology for medium power drive, okay, and multi-level converter for high power drive. That means 11 kilowatt, okay, up to above 100 kilowatt we call as a high power drive, and below that we call as a medium power drive. And those drives can be controlled by using two-level converter or by using multi-level converter. So these converter, when you have, there are different kind of control strategy. Okay. The AC drives, first it was came as a scalar control. Scalar control means like in our house, we have, you can say, we have a refrigerator connected to a stabilizer. Stabilizer only can change the magnitude of the food, and that is a scalar. And then came vector control, both magnitude as well as phase, both you can control. That is called the field-oriented control. That is also direct, or and then one is indirect. And after that, direct draw control came. So the scalar control, you can see that the scalar control is magnitude and frequency of the control variable. You can do that. And this is the one of the application of the scalar control, the irrigation pump. VYF method, I don't know, but I remember in our childhood, there was a star delta starter. So they used to start by that way. But nowadays, in the smart age, you need to have the complete control over the device. So this inverter can be used, okay, feeding this power. So if you see VYF control, it is economical and robust. That is why nowadays, many companies, they have started designing the single phase inverter for pump motor drives. Okay. And then no inverter, torque and flux are neither directly or indirectly controlled. And there are also, they use in the pump, fan, and centrifuge. So in 1969, there was a great scientist, Black. So he has given the theory of trans vector. The induction motor behave or want to analyze like a DC. That is called trans vector control. Because they want that induction motor is a very complicated machine and all parameters are interdependent. So they want to make it, this complete drive as a independent control. Okay, so that everybody can. So this one, independent control means you have a DC motor. You see, there is a field winding which is perpendicular to the armature winding. So whatever change you want to do in the field, it will not affect on the armature. Whatever you are doing in the armature, it will not affect on the field. That is why inherent decoupled machine, DC motor. So controlling this type of machine is very easy. That is why it is very popular in the servo application. So the vector control. So flux and torque are controlled independently like that of a DC motor. That is the main purpose of this vector control. And the thing is that when you have a switching converters, switching converter, when you are connecting to a switching load, then that time you will see that this converter, which is the switching converter, will create another kind of the reflecting wave. So anyway, that we are not going to discuss that detail into the. So if you are interested, you can look in some papers. Okay. So we have A, B phase, and this phase we want to model it like a simple DC machine. Okay. Because DC machine modeling is very easy. Why? Because all the variables, it is independent of your, you can say that the DC, all are independent control. Okay. They are decoupled inherently. That is why, if you see here, we have a ABC phase, and this is a starter and rotor. And I think all of you must knowing there are starter reference axis, rotor reference axis, as well as arbitrary reference axis. So this one, which is these three arbitrary reference. So arbitrary reference means it rotated synchronous. So with this, this whole, after a lot of solution, we can see a induction motor. So how to control the induction? This induction motor, you need to first derive the state space equation. So which is here is the state space representation of the induction motor, right? From here, you can see that each block you can develop. You can see that the three phase supplied to the drive. So A phase, B phase, and C phase. And then you have a torque change here. You see here, this is a simple induction motor modeling based on the previous equation. That's it. This equation, based on this one, this complete modeling is carried out. And after that, you see each modeling part we have written here. So this field-oriented control or the vector control, we can see here that both are independently controlled. So torque is dependent on IA and IA. As it is dependent on IA and IA, field oriented control. Okay. So this is our field oriented control, where it is torque component of current and then the field component of the flux of the induction motor. Now, if you see field-oriented control, we have an induction motor. So it is, I request that anybody has any doubt, any slide, you can stop. So I will immediately try to answer your question. So if you see the field-oriented control block diagram, we have a pre-WM inverter and the connecting to the induction motor through speed sensor. There is a speed difference, actual speed, and this is the estimated speed that is compared, and then a PI controller, then you get the IQS from plus ISK. So what is the difficulty here? Here you need to transfer from ABC to D. And then you require a lot of estimation and calculation. Where if the speed of the processes is not very fast, then you may get like a hanging in the computer. Okay. So if you see here is a PWM inverter. A MOSFET phase, the three-phase inverters have. And you can see that this is the controller. Okay. Controller means you get one signal, another signal you put a knot, you get a second. Then you can see that this is your calculation of ID. And this one is your D2 transformation. And so this one is our another theta and IQ calculation, IQS calculation. And then we have ABC to DQ transformation. And this is our control. And this is the model, complete model of the induction. So if you see here, each block are modeled separately. For example, inverter, you can model separately. Current controller, you can model separately. And the controller, you can model separately. And the ABC to DQ, that can be modeled separately. And QS calculation, that is also modeled separately. Then you combine together and complete became right. Okay, field oriented model. So the field oriented control, if you see here, is IQS is depend on the developer torque and the reference flux, and IGS is the rotor flux to the divided by LM. So when you see the field-oriented control, you have to estimate this theta. Okay. So this is where we say that direct and indirect vector control. Indirect, by which you estimate the system. Direct, you a flux sensor, and that flux sensing can be used. Okay, flux sensor information you can use in the controller. Now, if you see here, these are the speed, okay, in the radian per second, and this is the electromagnetic torque. And you can see here, this is the starter current. So then these are the simulation result of the speed. So in this simulation result, you can see that here the speed slowly it is increasing and then it is settling. Similarly, as it is going, and you can see that torque also it is coming down. So limitation of vector control is the advantage of DC drive to implementation direct torque plus control. Torque control is inherent, high accuracy and good response encoder is required. Then we will discuss the direct torque control. Direct torque and coordinate transformation are required. No current regulation tool, no encoder is required to measure the speed of the motor. And moderate accuracy and excellent torque response. Encoders is required for high accuracy. So when you see voltage source inverter induction, this is my DC link, and I have four switches, upper one and lower one, upper one, lower one. So these three leg, we have 6 number of switches. And 6 switches, you can have the each leg you have a 2 to the power 3 is nothing but 8 switches you get. Okay, this is A phase, B phase, and C phase, and I8 required 8 number of. So this out of 8 number of active voltage, 6 out of 8 number of voltage vectors, 2 are the V7 and V0. And the direct torque control, how you will control? We control within the band, and each voltage, they have to, or these voltages, they have to within that band. And in that band, the control of the both flux as well as the torque. Now, the torque production in an induction motor, you know that the torque is directly proportional to directly proportional to the phi ds or the flux of the motor. So, if you want to estimate this thing, then you need to find out what is the flux. Okay, flux is the integration of Vh minus ISR. So this is implemented. Then these are the flux and it controls within that bound, within that given bound. And we use here 2 hysteresis comparator. One is for flux, one is for torque. So you can see here, this is our upper one is our torque hysteresis comparator. And lower one is your flux hysteresis comparator. So here you can see that V ABC to DQ transformation, these are the equations. This equation simply you can make by using simulation. Okay, it is very easy. So very easy to model this system. Okay, so when you are finding out the flux, that time there are little challenges because this flux, when you are integrating this one, when the speed is very low, when the speed is very low, VDS is equal to 0. So the flux linkage is equal to minus IDSR. So it brings down the flux. So similarly, 5 also one model and 5S also and TE. Then we designed a optimum voltage vector table, and from this optimum voltage vector, so you can find out whether which switch will be on or which one will be on when you have a different kind of both flux and the torque. This is the complete motor. You can see here, we have applied a three-phase through a inverter circuit. Then we have a flux speed estimator, then torque estimation and speed estimation. And connecting to the hysteresis band, and it goes to the switching logic and back to the. So the starter flux, you can see here. This is the starter flux. This is our torque. You can see here. This is our torque, and this the second one is our speed, and then common mode voltage. Common mode voltage is a very beautiful concept. It reduces the machine vibration and it increases the duration of life of the machine. So what is a common mode voltage? Generally, in your house, you will find there are three pin plugs. One is your ground, one is your phase, one is your live wire. So if you see the grounding, also it is a ground system, that knob you will find that it is more thicker than this other knob. So grounding system is provided, okay, and that grounding and neutral voltage are called the common mode. Always, if you see, there are neutral voltage and there are phase the ground voltage. So ground voltage and the phase voltage, the neutral voltage. If it is ideal, it should be zero, but you will never find anywhere it is. So that is how this common mode voltage is one of the danger which create the common mode current. And this is the few the HIL hardware based research where we are transferring. You can see that the speed remains undisturbed even there is a change in the torque. Okay. And this is the block diagram of the direct torque method, direct control, that we have an induction motor, and this induction motor is fed by the three-level NPC inverter. And inverter supplied by a DC voltage. And in control block diagram, you can see here, both the speed as actual speed is measured with or compared with the reference speed, and the speed passed to the controller, the limiter, give her the torque, okay, reference torque. And from the estimation block, we estimate flux and torque. And this reference flux pass through the hysteresis comparator, and then based on the three status, the torque status, the flux status, as well as the status at which it remains. So the switching table, okay, will give you switching signal for this three. And how to model this one? Each part you model. Each part, for example, motor modeling we have seen. Motor is known to. Second one, the inverter model. Feed the inverter directly, you make it, and then you turn on, and then feed the DC, and just feed some load. So like that, each part is developed one by one by the complete unit can be developed easily. Then we have direct torque control. Why? If you see the torque DE is depend on the starter flux, rotor flux, and angle between them. So if you see the starter flux and rotor flux, the rotor flux will not do anything because the rotor flux is already the rotor flux is it is very difficult to find out. Whereas with no starter, you can control starter. But starter flux control is very strong. So what we do, we will only control the angle. When you control the angle, suddenly there is a dynamic performance in the system. Then there are different torque algorithm pattern, and this is the switching frequency, switching lookup table. Then this switching lookup table is modified and designed according to low switching loss. And this is, we have like a very big converter system, like this is a machine, the electric locomotive design. Okay. If you see the electric locomotive, you have a grid system. So the N is nothing but your grid. Actually. And then through inductor, it is connected to this. So what is this one? This is nothing but utility-friendly converter. So if you have a diode bridge and apply a 3-phase power, so what will the current? Current is like a, you can say that it is a spike current. Okay, it will draw non-linear by the converter. So what we do, we use all the switches are the IGBT switches, and these are the you need to model and control. And then another converter which is connected to the load end, and that converter can be connected to the induction motor. So that means you have a converter which interacts with the grid and the DC link, and another converter which connects from the DC link to the load. The control strategy is that both the converters are controlled independently. Front-end converter operate in the hysteresis current mode. DC link voltage controller ensures neutral point voltage, because in the multi-level converter, neutral point voltage control is one of the biggest challenges. And this control is very, very important. Okay. So the neutral voltage control they can manage to do by using breeder resistance or sometimes by using a chopper circuit. But we use here a breeder resistance. So motor side converter feeding induction motor operates under DT6 scheme. Now you see here, this is a control strategy. This is a front end 3-level AC-DC converter. And you can see that we measured the DC voltage, compare actual DC voltage, pass it through a PI controller. And then we have a hysteresis current controller. And that hysteresis current controller is connecting to this 3-level. Then we have an inverter here. This inverter is load end, or it is driving the induction mode. And this is the same direct torque control in this part also. And it is here for operating this machine. Now, complete setup is important by using Simulink. If you see each block, here we have a block which is a 3-phase synchronous link converter. And feeding this one to this our induction motor and direct control induction motor drive, and that is also feeding. These are shown here in this 2 block, front end converter and load end. And if you see the front end converter, it looks like this. You have a ABC is your input voltage, then a transformation block, and then complete control is modeled by using Simulink. And this output of this one will give you the DC-link voltage, complete DC-link voltage. And then the load end converter, you can see here. This is our one, which is one is our induction motor. Okay. This one is our induction motor modeling, and two is the estimator block. You can see here, two I have put. This is the estimation block. And three is our lookup table. And four is our level switching table. And this complete unit, you can see that below also, there are also two boxes are there. They are the robust flux observer and estimator or speed sensorless control can be utilized. So that complete unit is utilized, but we are not going detail to those elements. Only we are doing here one is induction motor modeling. Then the second one is our flux estimation, flux and torque estimation. Then third one, your lookup table, where you choose the particular voltage vector for switching on this, the drives. And the fourth one is our the switching circuit. Okay, the output AC. So if you see the induction motor here, I'll say one thing that induction motor modeling, and this one is a torque estimation. You can see you have a ABC transformation, everything is there. Then saturation block is nothing but your limiter. It will limit the voltage and the torque. And then we have a switching logic here. You can see that switching logic 3 number. You have to choose which one to be turned on. Okay. And then we have an inverter model. Inverter model, as I think all of you must be knowing, this one is your inverter feeding to this machine. So if you see here, this is the speed for forward motoring, then again reverse motoring, and then forward motoring again. So you can see that the motor could able to operate 4 quadrant operation, forward motoring, forward braking, and reverse motoring, reverse braking, which is most essential for a traction motor drive. And you can see that the DC-link voltage, whenever there is a change in the speed, the DC-link voltage have a spike here. Okay, here and here. So that is how this DC-link voltage is affected during the transient period. And then the hardware setup, or the design of the hardware is very important factor. Generally, when we design the hardware, we generally just connect wiring like I have connected long back, this wiring. Okay, you can see here wire. This wire, because of this wire, has finite stray inductance. This behave like an inductor instead of a wire. So you are thinking that, oh, I have connected my wires and it is very nice. But actually, it is not wire. These are the inductors you have connected to your switch. So inductor is connected to a switch means there is a storage element. That is why if you're switching between one switch to another switch, if your stray inductance is less than 9 nano Henry, then you can easily remove the snubber circuit from the device. Else, you need to put a protection circuit for that. So that is how you can see here. We have initially designed with the wire by using Mitsubishi IGBT and fast recovery diodes. And in the below, we put the power switches, and above the switching, all the controller for the switches, we put here. And when we put it here, and that's complete setup, then you can see that the hardware here, it is showing here, this hardware, although it is operated for a 3-level, but it is coming like a 2-level, and you can see that there are a lot of spikes, and this is not looking like a voltage waveform at all. So this is what the different fabrication is one of the biggest challenge in the power electronics. Simulation easily you can do, but this also very challenging. And that is why what we next do, we use this multi-level converter, and by based on the bus bar structure, we design complete bus bar is designed. And this complete bus bar structure, along with this one, we design this complete inverter. Here you can see this is a 3-level inverter where 7-layer bus bar structure on the top of this one, and this is controlled by each the switch, and the diode also used as those converters only. So how you can do? Emitter to gate, you sort it, and then you operate this by using use only 2 diodes, which is there in this semicron IGBT. Okay, this is we have dual IGBT module, and this is we design. And then these are the switching or the driver circuit. And the driver circuit also we design very nicely for this table operation. And then this is our induction motor drive, you can see here, and connected from this, and they are the voltage and current sensor, and feeding to this one, this complete drive. And these are the few result. You can see that this is a 3-level inverter. And if you see here, we have a front-end converter, another one is load and inverter. So if you see the front-end converter here, the simulation and the experimental, below is the experiment and above is the simulation. You see, I have changed my current or the load changes. You can see that both voltage and current are in phase and sinusoidal. That means this is a utility friendly converter. And you can see that detected simulation as well as hardware, both are the same. And then we have this simulation result here and hardware result here. When there is a step change in the motor side, if you have a step change in the torque, so the whistling voltage comes down, again it reaches to the steady state because of the closed loop nature of control. And this is the block diagram where the front end is controlled by one computer and the load end is controlled by another computer, and the complete unit is controlled independently. Okay, there is both the converter independently we control. Actually, it is not possible in that period of time where both the thing can be controlled independently, controlled together simultaneously. So if you see here, we have a 3-level NPC converter, then it is connected to another load and inverter and connecting to this inverter. If you see the front view of this from the top, these photos are taken. And if you see here, you see this is this converter, this computer controls this converter, and this computer controls this converter. And from this auto transformer is connected through this inductor. You can see there are 3 inductors connected to this one and convert to DC, from this DC to this converter. Okay, and this converter is connected to this load. Okay, there is a this induction motor. So if you see that, it's a very complicated network controlling, and this is what is will find with inside a train engine. This is the prototype, 15 kVA. Okay, this first one is 15 kVA, second converter is 15 kVA. But if you see within inside the train, that is more complicated than this. And this, if you see here, there are speed change. You can see this one, both simulation and hardware results are given. The above, you can see that there is a change in the speed. Okay, so you can see that there is also a reflection in this the hardware type. So both they look equally look good, and both are, you can see that both are matching, both simulation as well as hardware results are matching. This simulation and this one, and this is the flux trajectory and speed. And you see here, it is our laboratory where you can have testing facility, and this testing you can do by using, you can see that our inverter is controlling this induction motor, and from dynamometer you can generate any kind of torque profile. So the any kind of torque profile, whatever you require, you can just program it, it will develop the same torque profile. That is how we can completely control the system dynamic. And this is a three-phase as well as a multi-phase, both it is available. And there are hardware and both comparison are taken place. Then there are also few work we did on the wind and electric vehicle also. So this is the wind energy system, and you see this is we want this this work I did in USA. This is which where we installed this wind turbine there as a double fed induction generator. And if you see I have not put the detail of the modeling because I want to give a little flavor here. This is a double-fed induction generator, and we want independent control of the grid side converter and the rotor side converter. So which is connected to the rotor, that is called the rotor side converter. Which converter is connected to the grid is called the grid side converter. So grid side converter makes ensure you the unity power factor operation, bidirectional power flow, and you can operate at any desired power factor and low harmonic. And the load side or the rotor side converter ensures you the dynamic performance of production of kinetic energy, okay, controlling that energy and feeding real power to the, okay. So this way you can see that you operate this one as a leading power factor, and below one is the lagging power factor, and these are the different DC link voltages. And you can see that in the hardware, you can operate this converter both in the leading power factor, lagging power factor, and at a unit power. And this result shows the competence of this complete unit. Then we have a direct permanent magnet synchronous motor drive. And this you can see the front end, there are a 3-level NPC, and the load end also 3-level NPC connecting to the grid. So this also you can see that although the current magnitude changes, but they are always in phase with the voltage. And this is the beauty of utility-friendly converter system. And you can see below is your generator speed and power is nearly proportional to each other. And then DC1 and VDC2, there was fluctuation, but by using the chopper control, you can see that both are maintained at 400. And there are voltage sag also study we did. You can see that as soon as the voltage sag is there, because there is reducing voltage, you can see that the modulation index increases. And that way it change the output voltage. And then we have studied some kind of the fault ride-through property of these machines. And when there is a fault, like in India also, I have taken the Spanish grid code. So this one, it up to 34, around 54%, 60% voltage drop, it should be turned on. So that is what we did here also. And you can see that under those conditions, because of the closed loop control and by putting the chopper control, the DC link voltage actually remains. You can see that both the VDC1 and VDC2, they are maintained always. They both are maintained, and you can see they are balanced. So you here in the grid voltage, line voltage, you can see that when the modulation index is very low, you can see here this converter, although a 3-level inverter, that is behaving like a 2-level. That is what the beauty of this. And there are also some of the work we are doing, that multi-phase machine. And I think we don't have time. Now, if there is any question, I will be happy to answer.
So any of the participant, if you have any question, you can ask from sir, as it was a very nice presentation about the drive simulations and the role of the converters. So if anyone having any doubt, you can ask.
Sir, I'm Shaija. Hope I'm audible to you.
Yes,
sir,
yes.
sir, I have a doubt. Like, how will we give that reference value, theta reference, in practical case in your FOC, field-oriented control, that scheme you explained?
Yes,
No.
yes, yes.
How do we set it practically? Like the angle between the rotor and stator.
Oh, rotor and stator angle. We compute direct. There are two methods. One is our direct field oriented control, direct FOC, and indirect vector. Okay. So
Okay, sir.
in direct vector control, we take the theta directly measured in the air gap. Okay. So
Okay.
theta, it means we integrate this theta dt actually. So we get the omega, then we integrate that. Theta is equal to omega t.
Okay.
Okay. From
Okay.
there we integrate from the speed reference. So that is how we get this.
Practically both are possible, right, sir?
Yes.
Okay, sir. Sir, one more doubt. Sir, uh, is it easy to do that hysteresis control? There may be the frequency will be very high. No, that internal loop. No.
Yes.
So
So
when we are applying hysteresis controller there, no, there will be it will be switching very quickly. No, very high frequency, right?
the very high frequency will come when it is crossing the zero. If the error band, tracking error, E reference, a current reference minus actual current is our tracking error. When the tracking error crosses the zero crossing, that time the frequency is very high. So that is why we put a hysteresis band. You increase the hysteresis band, it will decrease your switching frequency.
Okay.
But if you decrease the switching frequency, then your hysteresis band may not be within that limit. It may cross also sometime. That is why there is a proper tuning, proper way of design hysteresis band is required. That is why those formulas we have given, that formulas will give you the detail about how to design.
Okay, sir. Okay, sir. Thank you. Okay. Thank you, sir.
So any other participants, if you have any question? Because sir is having the sufficient high experimental exposure. So if you are having any doubt related to that also coming to your mind, you can ask. I think now doubts are not there.
If anybody has any doubt, you can also send anytime. Whenever you will get time and you come across something doubt, then my email address, I think I can just rkb @ iitp.ac.in. I put in the chat box, so you can ask anytime. Take.
Okay, sir. Thank you. Thank you very much.
Okay. So thank you, sir, very much for your very nice interaction to the today's session. It was very nice experience for the participant and for us also. Now, thank you, sir.
Namaste. Thank you, sir.
Yes, very much. Thank you, sir. Okay, sir.